mornings come, you watch the red sunrise. The LED still flickers in your eyes.
Hi guys, my name is Nako Nakatsuka. I'm a 4th year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. The stabilization of dienes by conjugation may be rationalized by resonance and molecular orbital descriptions. And so we already talked about resonance in the chapter before, but let me show you that again right here. A resonance description, such as shown here, involves charge separation, implying a relatively small degree of stabilization. So if we start out with this molecule right here, and then we show resonance where we have CH2, CH, CH, and CH2. Now we have a lone pair on this guy, we have a positive charge on this carbon and a negative charge on this carbon. And this resonance implies a relatively small degree of stabilization. It does indeed affect the stabilization of dienes. So now let's look at this diagram. A molecular orbital model for 1,3-butadiene is shown right here. So I'm going to write 1,3-butadiene. Note that the lobes of these 4 p orbitals have different colors, and they're colored differently because they carry either a plus or a minus sign. This distinction refers to different phases defined by the mathematical wave functions for such orbitals, which I won't get into right now. Regions in which the adjacent orbital lobes undergo a phase change are called nodes, right here. And there's an orbital electron density of 0 in such regions, called the nodes. Thus, a single p orbital has a node at the nucleus, and all the pi orbitals shown here have a nodal plane that is defined by the atoms of the diene. So this black line right here indicates the nodal plane where there's 0 electron density. This is the only nodal surface in the lowest energy pi orbital, also known as pi 1, right here. So since the energy is increasing right here, you can tell that the pi 1 is the lowest pi orbital, and then pi 2, pi 3, and pi 4. And then the higher energy pi orbitals have an increasing number of nodes. To finish off examining the dienes and why different structures provide more stability, and why in particular 1,3-butadiene is the most stable out of the different dienes that I showed, let's examine the molecular orbitals. So in order to have a conjugated system of atomic orbitals in which all the 2p atomic orbitals are parallel, such as the diagram that I showed you just before, all 4 of the carbons of the diene system must be coplanar. And this means that there's only 2 ground state conformation of such a conjugated diene, and one is called S-cis and the other is called S-trans. And the cis or trans designation is based upon the relationship around the central, formally single carbon-carbon bond, so this carbon right here. And so the S-trans conformation is more thermodynamically stable because the S-cis transformation has a steric repulsion between the 2 inside hydrogens right here. So as you can see, the distance between these 2 hydrogens is 2.21 angstroms in the S-cis case, and then in this case it's 2.5 angstroms for the S-trans. So this guy experiences more strain. However, both conformations are found at least to some extent. You'll see that S-cis is less likely, it's 5%, S-trans is 95%, and thus K equilibrium is greater than 1 since we would get more products. This image of the molecular orbital diagrams may also give you a better picture of what it looks like, how these different structures are both planar but have different configurations that allow them to have different stabilities. To summarize the 2 examples I gave for understanding conjugation, first of all, adjacent, overlapping p orbitals allows for 1, more resonance. 2, more electron delocalization. 3, lower electron energy. And the sum of this all leads to greater stability. So as an example, what we talked about was having this structure with the pi sigma pi conjugation is more stable than this structure due to adjacent overlapping p orbitals, which, as a result of all of these three factors, increase stabilities of molecules. Also, the consequences of p orbital overlap involve the first thing being the atoms with the p orbitals must be planar, like I showed you with the cis and trans configurations. Also, there's partial pi bonds. If you look back to the diagram that I showed you before, there were pi bonds that were pi 1, pi 2, pi 3, and pi 4, all different in energy, right? There's the bonding and anti-bonding pi orbitals. And finally, there's barriers to rotation. So depending on the configuration of that particular molecule, it's going to have a consequence of its p orbital overlap. So from here, I'm finally going to give you a proper definition of conjugation. And conjugation is the special stability which involves decrease in electron energy provided by electron delocalization in 3 or more adjacent, parallel, overlapping p orbitals. So let me write that down for you. This is special stability resulting from a decrease in electron energy, as I mentioned right here, provided by electron delocalization in 3 or more adjacent, parallel, so that it's in the same plane of the board, and overlapping p orbitals. And the overlapping p orbitals is not necessarily limited to pi sigma pi orbitals, as long as you have 4 carbon pz orbitals.